Good afternoon, everyone. It's my incredible privilege this afternoon to introduce my colleague from the 3AI Institute at the ANU in Canberra, Zac Hatfield-Dodds. Zac is a researcher at the 3AI Institute, which is building a new applied science to manage the machines, AI, cyber-physical systems, and other new technologies. He started using Python to analyse huge environmental data sets and contributing to libraries like Xarray to make such analysis easier for all scientists. Now, as a maintainer of Hypothesis, PyTest and Trio, Zac is still passionate about making it easy to write software you can understand and rely on. When not at a computer, he can usually be found surrounded by books of all kinds, somewhere out of phone range, or both. Please make Zac welcome.
Microphone on, might help a little. So thanks so much for that welcome, Kathy. I no longer need to introduce myself because it turns out I already wrote an introduction for the abstract page. I'd just also like to say thank you to all of the other people from the 3AI Institute who are here today. And if you're interested in that, come talk to us because we're running our new master's program in applied cybernetics next year as well. But let's get into the deep dive talk that I proposed on sufficiently advanced testing. I'm going to be talking through 4 parts here, which is based on how I actually started to think about what would make a deep dive talk. This came out of the feedback from last year's PyCon Australia, where people said that they would really appreciate more expert level or deep dive content. But of course, because they haven't happened before, I had no examples to base my own talk on. So what am I going to try to do today? I decided that I would pitch this for an audience which was comfortable coming to a talk advertised as expert level. So there will be some terms that I'm not going to explain from first principles. But I'm not aiming to require any specific expertise or experience with advanced testing frameworks. The whole idea is that this is the introduction for experts in other things who haven't learned as much about testing as they would like to. My goal is to focus more on ideas than specific tools, especially because many of the ideas do not have a corresponding tool in Python, at least not yet. To change how you think about testing, and right at the end, to give you a single concrete takeaway, something that you can implement on Monday to ensure that whatever your project or product is better tested than it was before. So the talk, in 4 parts. First, I'm going to talk about the state of the art of testing, how we come up with test cases, and how we can make computers do it for us. I'm then going to give a bit of an overview of how a project called Hypothesis that I work on is implemented, what it actually takes to put these techniques into practice with reasonable efficiency. My favourite section, perhaps, is the third, where I talk about techniques I think of as indistinguishable from magic. Things which are just super cool, so cool that it seems they can't possibly work, and yet, I won't say they do, but they might if we implemented them. And then last of all, of course, I did promise a concrete takeaway. So there will be that call to action with a specific thing that you can do on Monday. So, for the purpose of this talk, I'm going to define testing as any technique where you assess whether or not your code is correct, whether it's doing the right thing, by actually executing the code. And this is quite restrictive among the range of all techniques that we could use to assess whether our code is doing the right thing. So we could, for example, use a tool like MyPy for type checking. So we annotate our code. For each function, we declare what type of argument we expect for it. And this tool can actually read our source code and determine if there are any places where we're calling that function with a type that we didn't expect. This is actually really useful, but it's not testing. One of my favorite techniques is getting enough sleep the night before. I find I write much better code and many fewer bugs if I'm not sleep deprived. I also get twitchy if I have too much caffeine, and if I hit the wrong keys, that usually doesn't help either. Code review is another great one. And that can be human code review, a workflow that's become familiar to most of us through GitHub, where you propose a change to some project and a different human, not the author of the change, has to review it first. And the exact process of code review varies between projects, but the fundamental idea is that at least one other person thinks it's a good idea to merge that change. I, at least, find that very useful as the author of changes which should not always be merged yet. But today, testing. So how exactly do we write tests? How do we work out how we execute our code? The traditional way of doing it, which most of us would be familiar with as unit tests, is we think of some input for a function. So for addition, we might try to add 1 and 2. And then we call our function, add 1, 2, and then we assert that we got the expected result. That is 3, at least if I'm implementing addition. But this has a couple of challenges. The most serious, I think, is actually the one written on the slide, that I don't know about you, but for me at least, if I think of an edge case, I might write a test for it, but it's probably not one that I completely forgot when I was writing the code. And so, however carefully I think about things or how many test cases I try to write, there are certain things that would just never occur to me to test. And sometimes that's because I truly don't understand the system that I'm working with. I'll give an example of that later in the talk. But even before we get to this kind of fundamental challenge, which, yeah, it seems really serious, but it doesn't really seem likely to come up that often, we have this other one, that humans don't scale as well as computers do. So for every test case that we write, a human actually has to sit and think carefully and type it out. And so while this kind of auto-manual testing, automated execution, but manual creation, is really useful for regression testing to make sure that known bugs don't re-enter our code base, or for testing edge cases where we suspect that bugs might occur in the future, I actually don't think it's suitable as the only form of testing that we do. And whether that's what you might call unit testing of very small functions or integration or even end-to-end testing, the kind of test where we specify exact inputs and outputs doesn't scale as well as I think we need our tests to scale. So what could we do instead? One great, cute option is exhaustive testing. And conceptually, this is really simple. All we do is we execute every possible behavior of our code, and we check that each one's correct. Of course, there's two problems here. The first is that we probably don't have time to check more than a tiny fraction of the possibly trillions or infinite number of possible behaviors. And the second is that it's really hard to tell whether the behavior is correct. If you don't compare it to an exact output, how do you know whether you got the right result? And of course, this gets even harder when your requirements are fuzzy. We might call them business logic, or user interviews, or hallway usability testing. And if you're on extremely hard mode, the requirements might even change over time. And building a system where the exhaustive testing takes longer, much, much longer than you expect to have before the requirements change, does not sound like much fun for me. But there is hope. And that hope is that there are actually ways that we can work out what all possible behaviors of our code would be. So mathematically, we could think of code as being a kind of finite state machine. So it gets some sequence of inputs and it has some state in its variables or its memory, depending on how you represent it. And we can mathematically reason about equivalent sets of inputs. So in principle, at least, it's possible to get complete test coverage to try everything, or at least something which is equivalent to anything else we could have tried, without actually having to test every possible logical input. And the oldest trick for this is simply to put complete garbage into the program and see what happens. For any image parser, for any network library, for most command line tools, putting in random input should not cause it to crash. It should either do something, hopefully something useful, or emit a specific kind of error code, maybe throw a particular exception in Python. So let's consider how this might work, right? If we think of a very simple kind of program, right? This program only does one thing. It's a single function, and you call it with a string of bytes. And then it returns true if it worked, or false if it didn't work. Conveniently, most programs are implemented on digital computers which operate on bytes. So the idea of thinking of a function which takes bytes actually matches up surprisingly well with a lot of programs that we're actually interested in. Compiled programs, for example, almost always operate on bytes. And so the oldest testing technique in the book, once the human testers had done their work, back in the days of Fortran, but before jokes about real programmers only using Fortran, because Fortran was the only language that was not assembly code, where you had to write in raw hexadecimal. You would take a deck of punched cards, perhaps from an earlier draft of the program or perhaps from today's database dump for payroll, and you would shuffle it up so that it was nicely out of order, and you would feed it into the computer. And if the electromechanical computer stopped, you had found a bug. And in those days, a bug might even be a physical insect caught in the machinery. If there's anything that we got out of Moore's law scaling things down, the upside is that bugs are now too large to fit inside our CPUs. But this is an old technique. So the image I've chosen to represent it actually predates digital computing entirely. These are punched cards from a thing called a Jacquard loom, a tool of the first industrial revolution where English textile mills first learned to automate not just the weaving of cloth, but the weaving of particular patterns of cloth. And so the roll there that was produced entirely by a machine would have previously taken years of skilled labor and now only a few hours. And of course, there was an anti-tech backlash then and the coining of the word Luddite. When I'm talking about randomness, though, there are a couple of different things. And I realized when I was giving an earlier version of this talk, just to test it out, that I'm using the word random a lot. We can put in random inputs. We can deal with random programs without actually defining the word random. And one of the lovely or terrible things about the word random is that it can mean so many different things. So when we talk about randomness in computing, we might mean numbers which are truly unpredictable, that come out of some kind of physical phenomenon that we can't predict or understand well, or guess what the next number will be. And so one of the coolest things on the internet as a source of randomness is at Cloudflare headquarters, they seed some of their random number generators with a video pointing at a wall full of lava lamps. And so there is this wall full of lava lamps that helps keep the internet secure, and I just love that. But if you don't have a wall full of lava lamps handy, there are still ways that you can get numbers which are sufficiently random. Or maybe you're even doing something like a statistical experiment, a simulation, where you want to be able to reproduce it later and know that your results were not just a coincidence, but your code was actually working, and maybe you could even fix a bug in your code and run it again and get the same results. You can't do that with true randomness, but you can do that with what we call pseudo-random number generators. And so these are very complicated programs which will jump around the numbers in a very unpredictable way. But if you set the internal state to something particular, you'll always get the same sequence of numbers out when you drive it. So Python's random module is actually a pseudo-random number generator. And if you're thinking of doing something with security, you should not use it because it's not truly random. You should instead use the secrets module, which is suitable for secret things. That's because Python doesn't have what's called a cryptographically secure pseudo-random number generator, which is far too many words to describe a simple thing. It's a sequence of numbers where you can't predict what number will be next, ever, simply by observing them. I think that's probably enough now. This is a set of dice. They're, depending on how you count, random, pseudo-random, or not really random at all. And the interesting thing about dice is you might think that there's an even chance of each number coming up each time you roll dice, right? But if you have dice like this that are not perfect cubes or not tossed by a very random robot, it is actually likely that certain sides come to rest face up more often than others. So if you have a heavy die, for example, with divots out to indicate the numbers, if you roll it completely randomly, it is slightly more likely to land with the 6 upwards, because that side is slightly lighter. But we wouldn't say that the die is non-random. We would say that the die does not have a uniform distribution. And so for a thing to be random, it is not necessary that every possible outcome be equally likely or have any other particular output. It need not be like a bell curve or an exponential curve or any other curve or step function. It is sufficient that it's difficult to predict the next thing for me to colloquially call it randomness. Everyone following so far? Glad to hear it. And so with that digression about randomness, let's go back to thinking about programs. How do we work out what programs actually do? One answer in Python and in other languages is to use tools which measure code coverage. And code coverage tools fundamentally answer 2 different questions by instrumenting your code and checking which part's executed and logging that somehow. And those 2 questions are, first, what just happened? And second, what didn't just happen? And this, it turns out, is surprisingly useful. If we know what happened, we can track what logic in our code was actually executed. You could use this in production to work out which parts of our code are most important to optimize. Or you could do the converse, and at testing time, you can look at what parts of our code were not executed by our tests. If our test suite did execute some part of the code, it's possible that it still wasn't well tested, that it was executed incidentally when we were checking some other piece of functionality. But if a particular function was never executed at all, we can be pretty confident that it was not tested either. And so there are different levels of granularity or different levels of detail that we can measure coverage at. The simplest is function level. Decorate every function, every class, every method, every module, and just see if it gets executed. This is fairly useful, but in Python we can do better than that. Coverage.py, one of the leading Python modules, can actually hook into the interpreter and report for each line of code, was it executed or not? These days it can even hook into some more detail and go, for each test function, which lines of code were executed. And this lets us go through and determine, for example, that the else block on some if statement was never executed because the condition was always true. Useful to know if you're looking to delete code or work out where you need additional tests. Or we can even go to branch coverage. And branch coverage separately tracks each side of an if statement. So if we had an if without an else, and we always have that statement as true, branch coverage can tell us that we don't actually need that if statement. It's always been true. You either need another test where it's false, or you can delete the conditional. Coverage metrics are often in testing compared to a kind of maximum possible coverage, which we get from analyzing the source code. So we can go not just, here is what was executed, but here is what could have been executed. And then can I just see a show of hands? Who here has ever used a percentage coverage metric? Awesome. Who here really loves percentage coverage? A few hands. I'm not a huge fan. It's a good indicator of the rough state of your code base. But if you're using a threshold for coverage, something where you say, for example, we need at least 70% coverage or at least 90% coverage for this pull request to be accepted, unrelated refactorings can actually make that number go down. If you delete trivially covered lines of code, code which is not doing anything useful but is still executed by tests, then you can make your coverage proportion worse. And I don't know, maybe this is old-fashioned, but if I'm tracking some number that I think represents my code quality, I don't want it to go down when my code quality goes up. So if you can, try to get coverage to spit out an exact number of uncovered lines and mandate that that never passes a particular threshold. Or you can simply annotate your code with no cover bits on the parts which you don't mind being uncovered and then require 100% coverage. That's actually my preferred technique because it forces you to make an explicit decision and one which you can grep for in your code base to find which parts of this code did we decide were not important enough to test. When you put these ideas together, tracking of coverage and then random inputs, you get a technique called fuzzing. Has anyone heard of fuzzing? Couple. The rest of you are in for a treat. Fuzzing is the idea that uniformly random inputs, the kind we would get from shuffled punched cards or from piping dev random into our binaries, is unlikely to find any but the most trivial bugs. Almost all possible inputs will simply trip across some validation logic. In an image parser, it might be the bit that checks, does this file start with %PNG? If not, it is not a PNG file. And your chance of random bytes matching that string is 1 in 256 to the power of 4, which is a fairly small number. And so what we can do instead of putting in uniformly random bits, we can use a genetic algorithm. We can actually instrument our programs to watch the coverage, tell what behavior is being executed, and then start by putting in random things. And then we find an input that does something a little different to the normal. We can take that input and mutate it a bit, change it around, put it back in, see what happens, combine it with another one. And pretty soon we're likely to find that an input which starts with a % sign for %PNG does something a little different. It goes down a different branch. And then when we add an N, it does something different again. And before you know it, you've developed this testing tool which will synthesize valid images for you out of thin air, just by watching the behavior of the program that's meant to deal with them. So, based on that feedback, coverage as a proxy for how much code is this executing and what code is this executing, we can drive up the chance that we execute some part of the code which, well, that's the problem. The only thing we can detect with a fuzzer is a crash. And so the second part of this trick is a collection of ways to make bugs in our programs correspond to crashes instead of silent misbehavior. In compiled languages, there are many sanitizers which will do this for addresses, for memory violations, for undefined behavior. But the one that's common across all languages, including Python, is assertions. So an assertion, my favorite definition, is an assertion is a statement in a program which will do nothing unless there is a bug. So an assertion is something which should always be true. It might or might not be executed depending on how you run Python. But if it's false, then it'll throw an assertion error. And that exception will propagate, and you'll get a crash. Or your test will fail. This means that when we evolve bad inputs, we can check not just do we have some kind of error which forces us to crash, but do we trigger any assertion that we had? And so if you start and end your functions with assertions, that the input is roughly what you expect, that the output is sane, that things round trip or in canonical formats, you can often uncover your own misunderstandings or your future self's misunderstanding of past code simply by running the same tests against it. So that's part one. We can go from complete randomness to generating things which are very likely to find bugs, which would seem impossible by mere chance. So it's time to get back into Python a little more. And I'm going to talk about the implementation of a tool for property-based testing. I'm going to start by telling you what property-based testing is not. Property-based testing is not just trying a very large number of tests. This is a super useful technique. On GitHub, you can find the big list of naughty strings, which is a text file several thousand lines long. And every line is some bit of text which has caused a bug in some other piece of software. Some of them are SQL injection attacks. Others are cross-site scripting problems. Some are just emoji. And I really wanted to put one in here, which is Hebrew text, which changes the direction. First it's left to right, then it's right to left, then it's left to right again. But when I put it into my slides, PowerPoint crashed. So I don't mean to diminish the value of this kind of testing, right? If you're dealing with things which should accept arbitrary strings as input, grab the big list of naughty strings, try them all. It's really easy with something like a PyTest parameterize. But there are a couple of problems which would make us not want to do this for literally everything, right? First of all, someone has to come up with the big list, and they accept pull requests, so you can help out with that. But the corpus has to come from somewhere. This is great for things which have multiple implementations or are implemented in multiple languages. But when we find an error, the one that we find will tend to be relatively complex. If you've found something through this random process of fuzzing, the thing that triggered a bug tends to be really nasty to debug. And as we all know from Stack Overflow, we should be posting minimal, complete, reproducing examples, right? This will just give you a reproducing example. Better than nothing, but not ideal. So property-based testing is the idea that when you combine random inputs, and in property-based testing, they're usually specified by the programmer in some way. So instead of saying, give me literally anything, you would say, for example, give me 2 integers between 0 and 100. And it would try many combinations of those. And then instead of asserting that your code output a particular exact result, which you don't know because you don't know what the exact input was, you can make some assertion about a general property. For example, no matter what data I get from the user through this form, I should be able to save it to the database and then bring it back. And I should have the same data, no matter how many times I save it to the database and bring it back. Or you might have something where if I convert it from JSON to XML, then back to JSON, I get the same data. Or this becomes really powerful if you have other properties. For example, we're re-implementing it. We can feed the same input into the old system and into the new system and assert that the new hotness gets the same result as the legacy version, or that the single-threaded version has the same behavior as the multi-threaded version. Has anyone here ever been bitten by a multi-threading bug? Yeah, it is a useful test. And there are other properties as well. So for something like a scientific simulation, where the whole point of running it is we don't know what the output should be, we might still have some other clues. In thermodynamics, we would know that if we start with a higher initial temperature, the final temperature should probably also be higher, and vice versa. If we're building a self-driving car, we might say we don't know exactly what it should do, but if we simulate adding a raindrop to the camera lens, the car should not crash. Or the car should not confidently decide that it should turn across oncoming traffic. I draw that example from a recent paper which I don't want their self-driving cars. And at this point, I owe you a really quick overview of Hypothesis itself. It's a library in Python for property-based testing. I'm a core developer, so I might say it is the library in Python for property-based testing, mostly because I don't know of any competition. All of the core developers are volunteers, and in fact, there are no non-volunteer developers. We have great documentation and focus a lot on usability. So whatever your concrete problem is that you need to solve with Hypothesis, we have probably solved it and documented it. But this is not a talk about Hypothesis so much as a talk about the general family of testing techniques. So if you want to learn about that one, I've given other talks you can find on the internet. But here I'm going to talk about the implementation, how Hypothesis minimizes examples, then how Hypothesis runs its test, and finally how Hypothesis generates inputs. This is completely backwards, but I promise it makes more sense backwards. So our first challenge, right? I mentioned this, that Stack Overflow will ask you for a minimal example, is that if you use Hypothesis and find a bug, I don't have enough time to come around to your office and hand minimize it for you. So we need to automate that process somehow. Fortunately, because we're dealing under the hood with strings of bytes, we can automatically try to minimize it. While it's not always clear what might make a more minimal example if we're talking about nested dictionaries, for example, if we confine ourselves to strings of bytes, there are a couple of pretty clear heuristics we could use. The first is that shorter strings are simpler strings, right? Less input is simpler. And the second is that among strings of the same length, we can break ties by imagining them as integers and going with whichever one has the lower integer value. So we tend to prefer zeros to ones, for example. And so if we imagine for a moment that we can operate on byte strings, we have a couple of convenient things. The first is that every input is unique if we're dealing only in byte strings. Every input can be ranked in comparison to another candidate input. And this means that it would be valid to simply go, this is the byte string that found a bug. Let's try just chopping it in half. Does the first half only find the same bug? What about the second half? And we can do a sequence of these operations. Analogously here, the dotted lines between dots. Dots are executions of the test. The dashed lines indicate what we try to mutate that input and make it smaller. Given any possible change to that input, we can tell whether, if the test still fails in the same way, it would in fact be simpler. If it's not simpler, we don't even have to run the test. We can just discard it. And by running them, we can slowly evolve our way down, not necessarily to the simplest possible bug or the simplest possible input that triggers that bug, but to a very much simpler one. Now, there's a couple of benefits of this. If we look at the diagram on the right of this binary tree, all of these, we'll say, trigger the same bug. And going around clockwise, we've simplified it. And by the time you see the one on the bottom left, if you look at that and you think, I have some bug in a binary tree function, the bug might be related to the fact that the binary tree is unbalanced. And in particular, when you look at that, you can go, if it was possible to simplify it further, it would have been simplified further. So it must be something about the unbalanced nature of the tree. So while this is not strictly required for property-based testing to be useful, in practice, test case reduction is a really, really important feature to make people enjoy using the tool. Let's go through to the middle part. Here, we think about how do we treat unit tests as if they were fuzz targets. I've said before, right, that we could think of any program potentially as taking some string of bytes as input and doing something. And so that's effectively what we do. Hypothesis gives you a decorator, which internally wraps the test, and we'll try, first of all, rerunning every previous byte string that we've seen cause some particular bug. So you don't have the usual problem of random tests that if you execute the test and then execute it again, the bug may or may not happen the second time. That sucks when you're debugging, right? When you're never quite sure if you've fixed it or if it's just decided to go away until tomorrow or next week or 3 a.m. So first we replay all of the existing bugs, and then we generate a bunch more random bits. So we do the kind of mutational fuzzing. And for each of them, we just call the fuzz target. And if there's an exception, then we grab whatever input caused it, and we do the reduction step. Making sense? Good. And so the only wrinkle here, right, is how do we go from strings of bytes to the objects and the values that we actually use in Python? And there's a couple of neat tricks. The first is, of course, that in a computer, everything is secretly bytes under the hood, right? Numbers are bytes, strings are bytes, lists are different bytes, dictionaries are bytes. Everything is bytes. And so all we need to do is convert our bytes into some more meaningful value. This is a known category of software, and they're called parsers. And so a parser is a thing which takes some sequence of bytes or text and converts it into other values for us. And my favorite API for this, which we use in a hypothesis, is something called a parser combinator. So a parser combinator is a function which takes a couple of different parsers potentially and sticks them together somehow. Most simply, you could, for example, have a parser which is the list parser. And so it recognizes an open square bracket, and it knows to look for some value and then a comma and then another value or a closing square bracket. And so that's all the list parser needs to do. So to get a parser for some particular list, you need to tell it how to recognize individual elements. And so in hypothesis, we also have an integers strategy, or a parser. And so to get a list of integers, you take the lists function and you parse it integers. And optionally, you can tell it how long you want it to be. And so we implement strategies under the hood in the private API as classes which just have a getBits function. So all they do is look at the next part of the input and then convert that, if they can, into whatever their output type is. Most of the strategies that we provide, though, don't even have to do that. We can implement them in terms of other strategies. And that's the public API too. You define your own strategies for whatever type or class or collection or specific kind of data you need to call. So below that, there are a couple of other tricks we use. And I'm skipping over so much of the cool stuff about how you can generate Django models or pandas data frames or things accepted by a regular expression. Like you can take a regular expression and hypothesis will give you strings that match the regular expression. It's super cool. And that bit wasn't in my notes. It's just so exciting. Under the hood, there are a couple of implementation tricks that are quite important. The first is that whenever you define a strategy, if you're in the internal API, on the public API, we make sure this mostly doesn't matter. But internally, we try to implement all of our strategies in a way that shrinks well, that allows the reducer to make progress using the operations that it knows about. So one example of this is when we're generating a list of something, the natural way to do this might be first get a number to decide how long the list will be, and then get that many elements and put them in a list. The problem is when it comes to reduce it, to successfully reduce that one, you would have to simultaneously reduce the integer by 1 and delete a list element. And in general, this is going to be less efficient than what we actually do, which is we calculate, given our expected list length, with what probability should we add one additional element? Then we draw a number, and or draw a Boolean with that probability, and if it's true, then we get that element. If it's false, we're done, and the list is over. And that means that instead of having to delete or change two parts of the byte string in combination at the same time, we can simply delete a region and it will locally have that effect. Defining test case reduction in terms of strategies rather than having to define something specific to, for example, each type of number gives us a couple of other examples. If you imagine your test only takes even numbers, for example, With hypothesis approach, you can simply take the number and then multiply it by 2. And that strategy will then only give you even numbers. But when it shrinks, every number it tries to produce will still be even. If you're using something like quick check in Haskell, you actually have to put another filter in place in your test to make sure that when you generated even numbers, it didn't try to shrink by feeding you odd numbers. That tends to get you unrelated errors, which is not fun when you're debugging. If you're wondering about the performance of this, come talk to me in the hallway track, but in short, premature optimization is the root of all frustration in testing. That's a lie. There are lots of other frustrating things, but it will be frustrating. It's fast. It's certainly fast enough. And so now we get to my favorite section of the talk. The cutting edge techniques that, to my knowledge, are not available in Python, nor widely used at all. Sadly, at least if you're an enormous nerd about testing, there's this vicious cycle between having very few users, the tooling not being awesome, very few users, very few developers, the tooling is not awesome, no one uses it. We can change this together. So if you're interested in these techniques, consider that people have not tried investing significant effort in implementing them and found it's too hard. In most cases, a paper has been published and then they've not been tried at all. So if you want to invest a week in trying to implement them, you could get somewhere really cool. And finally, for each of them, if people are still awake, I hope you're still awake, we're going to have some audience votes. At the end of each slide, I'm going to ask you, is this technique fantastic and we should use it? Flaky and it might work but only sometimes? Or futile, it just doesn't seem worth the effort? Can I see a show of hands for fantastic? Okay, some people are excited. For flaky? No one's flaky, that's good. Futile? No one's futile either. Oh, one person. I'm sorry. It's not that bad. Yep. First technique, swarm testing. This one is unusual among the more advanced magical techniques in that it doesn't actually use any feedback or inspect your code at all. This one simply finds more bugs with the same property-based tests that you already wrote. Magic, right? The way it does this is by going, traditionally property-based testing would do a kind of uniform random exploration based on the state machine or the grammar of the inputs that were described. So if you said integers, any integer was equally likely. If you were operating on a stack, for example, you would be about equally likely to push elements onto the stack or pop them off. And what this means is you're extremely unlikely to exercise the really weird edge cases. If it's equally likely that you add something or subtract something, it's very unlikely that you do 50 of one in a row and trigger some kind of overflow bug. And so what swarm testing does is it generates what the authors describe as a swarm of configurations. So many different probabilities, for example, between adding and subtracting. And then each time we go to generate an input, we pick one of those, and then we generate the rest of the input. And so this would make it more likely that we generate weird things, diverse things, things which are unlike anything else our code has ever tried. It's a way of making property-based testing more creative. So, does this seem fantastic? Flaky? Futile? We seem tired on it's either fantastic or a little bit flaky. So it's at least situationally good, right? For what it's worth, I tend to agree. The advantage of this one is that it doesn't require any configuration from the users, right? The user doesn't even need to know that swarm testing exists, let alone what it's called or how cute ladybugs are. And at worst, it should be kind of harmless, right? It doesn't seem like changing the distribution of our random inputs would hurt, even if it doesn't help much. So why haven't we implemented this in a hypothesis? We'd have to change the underlying model that we use quite substantially. We plan to get around to it at some point, but we're all volunteers and have no free time. So technique number 2, targeted property-based testing. It's basically regular property-based testing, but we add one thing. Instead of tracking coverage the way that fuzzers do, we give users an extra part of the API, a target function, where they can feed in some floating point number to tell us how weird is this input? How large is it? How complex is it? What's the compression ratio? And then the engine will preferentially mutate towards things which maximize that metric. longer lists, lower compression ratios, things which get higher antivirus scores. And so just as fuzzing evolves things based on the coverage, or eventually the number of bugs it's already found there, we would then evolve inputs which tend to maximize whatever target metric you choose to feed in. We actually tried doing this with coverage information in an earlier version of Hypothesis, but eventually took it out. And there were two reasons for that. The first was that while it was somewhat helpful, running under coverage is slower than running without coverage. And so when we looked at this, we thought if what people want is to find many bugs per second or minute or hour of time that they spend running Hypothesis, often you would actually get more bugs if you run it with coverage disabled, because it's 4 to 5 times faster. So making it twice as likely to find a bug for each test case, in fact, reduces the number of bugs we find. And the second is that the way coverage is implemented in Python, it uses a trace function. So extra code is called every time the stack frame changes in the interpreter. And this means that it's incompatible with many debuggers. And the time you most need a debugger might in fact be when you found a bug, and it was kind of fragile. So given that it wasn't helping much, we took out the coverage-based stuff, but we're quite excited about the possibility of targeted property-based testing. Who thinks this is fantastic? Who thinks it's flaky? Who thinks it's futile? Who hasn't put their hand up yet? Thank you. My opinion on this one is that it's a fairly fragile technique. While in certain situations it is impressively powerful, it also relies on the user choosing a useful target function. And often there isn't a target function which corresponds really well with bugginess. So we might be able to drive to particular extremes of our input space, but whether or not that actually helps us find bugs is kind of unclear. That said, we do have an open pull request implementing targeted property-based testing. So if you're really keen, you can install Hypothesis directly from Git and use it. Third technique, symbolic execution. Instead of executing your code with specific values, if you're using symbolic execution, you analyze the code. You calculate the different branches that can be taken through, and you make an exhaustive list of all the distinct paths through your code. So this is a little more tractable than exhaustive testing, right? It might be that for the purposes of your code, every positive integer is treated identically. And so with symbolic execution, you could analyze all of those at a single go. I'll admit that by my definition of testing where your code is actually executed, this is not testing. But bear with me. Does it sound good? Fantastic? Fragile? Futile? All of those are quite reasonable. In my view, this is somewhere between fragile and futile for large Python functions. While you can do it reliably for small functions, when you get up to larger code bases, you come into a couple of problems. The first is that Python is amazingly magical. You can override dunder methods. You can patch things at runtime. You can execute code that was delivered as bytecode over the network. And that means that it is really hard to be sure, just from reading the source code, exactly what Python will do. This problem is made harder by the fact that Python doesn't actually have a standard semantic definition. Python has a reference implementation, which means that by definition, Python is whatever the CPython interpreter does. And that makes it pretty hard to write a symbolic execution engine because the behavior of the CPython interpreter keeps changing when they keep working on it. That said, I really like symbolic execution. If only there was some way to make this work. Concolic execution is where we combine concrete values and symbolic execution. It's a bait and switch, right? We do symbolic execution for a while, and this is really cool and mathematical and abstract. And then we're like, oh no, we have no idea what to do here. We work out, well, what kind of specific actual Python value would have made it through this sequence of branches to get here? Then you generate it, and you call the code, and you see what happens. It's total cheating, and it's awesome. I won't ask you whether this is fantastic, fragile, or futile in Python, because I have no idea. To my knowledge, no one is doing this for Python at all, but it seems like it'd be really cool. I will note as well that in practice, Because the chain of branches can get very complex, we usually use what's called a SAT solver to work out what combination of values would actually get to a particular part of our code. A SAT solver is a thing which can represent, if your problem is represented as some set of simultaneous equations, so you have a set of variables and you set all of which are either true or false, and you have a set of equations, A and B or C is true, and not A and not D is true. A SAT solver will use various heuristics and various special techniques to try to find some set of assignments to those variables which satisfies all of the equations. So SAT solver is a thing which solves the Boolean satisfiability problem. This is amazing because that problem is NP complete. That means there is this class of problems where there is no efficient algorithm to find an answer, but there are efficient ways to check an answer. If you're thinking about the simultaneous equations, checking the answer is really simple, right? You just substitute in the values and see if all the equations are correct. But finding one takes time, which is exponential in the number of things you have. So SAT solvers are like in principle impossible, and yet they usually work. I have no idea how that happens, but I am so delighted that they exist. And the final technique, which I will admit I am also really excited about, is constructing programs. So not just thinking about a list of numbers or some particular file format, but getting our property-based testing library or our fuzzing tool to generate Python code itself. This would be pretty cool. We could test everything from linters or auto-formatters. Does the type checker work on arbitrary programs? We could check competing implementations. So CPython and PyPy could check that when they execute any program, they give the same output. And there are a couple of ways that we could do this. The first is that we could actually look at the grammar of Python source code, the thing which describes what tokens are valid after a for statement, for example. You need a colon, then you need some indentation, and then you can have other code. And we could generate arbitrary strings which would be passed by the Python grammar. I tried this. It worked, right? I found a bug in the CPython parser because it turns out that the grammar of Python is not exactly describing what CPython really does, foiled by the reference implementation. But there are other options we could use. We could instead try to generate a syntax tree and then work out what program source code corresponds to that syntax tree. So, super cool. We could generate programs, we could test our programming languages as well as the programs we write in them. Who thinks this sounds awesome? Who wants to work on it at the sprints with me? Woo! Come see me later. Final bit, right? I promised that we would have the section where I gave you something you could actually use. And for those of you who are going to help me with the last one on Monday, awesome. But for the rest of you, I've talked a lot about some cool tools and some great ideas, but can you actually use any of this stuff? Does anyone feel that they've got stuff they can use already? A few people. Awesome. I want you all to go back to work or wherever you're going on Monday and write some property-based tests. Sound good? I'm getting some nods and some blank faces. You're probably thinking, Zac, you've told us how cool you think these are, but you haven't told us how to actually write them. And you're right. You know step one? Step one is to install hypothesis. You type in pip install hypothesis. Or if you prefer conda, you type in conda install hypothesis. And there are a couple of things here. First of all, hypothesis is compatible with every supported version of Python from the PSF. That means that we support Python 2.7, but we will drop it at the end of this year. So if you are still using Python 2, you might want to think about moving to Python 3 soon. Hypothesis is compatible with a wide range of other things. We have very few dependencies, but many optional extensions, and quite a healthy community ecosystem of third-party libraries. So if you use NumPy, Pandas, Django, JSON schema, we have plugins that will deal with all of those for you. So you've installed hypothesis. You're going to do this, right? Yeah? Step 2, migrate a single test. You probably have a test in your code base, which at some point just has an arbitrary value in it. And you know that testing the add function could use more numbers than just 1 and 2, but you're in a hurry, right? So you typed the simple ones, or you didn't want to debug really complicated ones, and you were sure that 1 and 2 should equal 3. So find a test that looks something like this. This test is simply that if we start a new Git repository, and we create a branch called new branch to check out, then the active branch will be the new branch. This is kind of how Git works. So what happens when we want to abstract that a little more, generalize it, and not only consider the literal name new branch? Well, step 1 is simply to move arbitrary constants to keyword arguments. This test behaves identically to the old one. It doesn't depend on hypothesis. You can do this before step 1, though step 1 is great. And what we've got now is a variable, which indicates the branch name. And so our test semantically is saying, given any branch name, this should pass, right? The next step is to move that particular specific argument to a hypothesis strategy. So in this version, we are using a hypothesis. We've got the given decorator, and we have the corresponding arguments to given for arguments to our test function. And in this case, our strategy just generates the string new branch. We haven't changed the test semantically yet, but we have started to use the hypothesis. Then, of course, abstraction is great, right? Don't repeat yourself. So we'll extract that out to a separate function, which returns a strategy for valid branch names. And this means that we could reuse the strategy across any test that's using the names of branches. And when we eventually go back and improve that strategy, all of our tests will get more powerful. So if our requirements change, we have a single place where we can change to improve our tests. Then we can try generalizing the strategy. This is a strategy for arbitrary Unicode text. I will give you a spoiler and say that this one fails. It turns out you can't name a Git branch empty string. You can't name it space. You can't name it new line. You're probably not meant to name it master either. But master is a valid branch name. So if you actually read the Git manual for check reference format, you will see that the rules are extremely complicated and that they vary by both operating system and file system, because branch names are also stored as file names. So we're just going to take the easy way out and say, sure, we want text, but we only want ASCII letters, not even dashes or underscores, because there are rules about how many dashes you can have in a row in a Git branch name, it turns out. And we need at least one letter. You can't have an empty string as the name, and no more than 95 letters. Because some Git hosting websites arbitrarily cut off branch names at 100 characters, and branch names technically include head / as the first part. So between 1 and 95 letters gives us a valid Git branch name. What do we do then? It's at least possible that this will generate the string master, being 5 ASCII letters. And so we add at the top of our test function an assumption. An assumption or assume is a function from hypothesis, which is much like an assertion. But instead of indicating that the test has failed, it indicates that the input is problematic in some way, and just tells hypothesis, look, that one was okay, but don't give it to me again, and don't count that as a failure. Try again. And so we can make our assumption, right? We can say any sequence of letters, not the sequence master, and this test should pass. We've now refactored our test completely to use hypothesis, and chances are we've discovered and had to read something about the manual. It hadn't occurred to me, at least, to wonder what was a valid branch name in Git. Because I always gave my things sensible branch names, like targeted PBT, or working on that bug fix, or oh God, why is this happening? And the end result, once we finalize refactoring this, we might have a strategy for repositories as well. So that instead of creating a new empty repository, we actually say this property should be true of all of them. And so it's not just the master branch that we want to exclude, but we can say given any repository and any valid branch name, if the branch name is not yet in the branches in the repository, then checking out that branch means that the currently active branch will be whichever one we just checked out. This is about as close to a genuinely mathematical property as you will see in code which is not doing simple data transformation. You can test that stuff with hypothesis too, right? It's great, it's easy. But you can also test the more complicated stuff. And I hope I've convinced you that you don't have to write these from scratch either. You can find existing tests and incrementally migrate them to take advantage of something like hypothesis. When you're ready to take that final third step though, you can write a property-based test from scratch. For your first one, I strongly recommend choosing what we call a round-trip property. The best one is testing that when you write some data to a database or to disk and then read it, you get the same data back. This is something which should be true for basically any way that you store files or put stuff in a database, right? I hope you want the same data back. This one is really useful because there tend to be a lot of different layers. File systems have subtle rules about how large things can be or where they go or what they have to be named. And often, I discovered that I didn't quite understand what those rules were. If you don't have a convenient pair of write and read functions, you might be working on a networking thing. A send and receive is quite similar. Or if you're working on a simpler project, a set and then a get of some property. Just testing that when you round trip this, it always works. So let's go see a worked example. This one's pretty simple. We're testing that if we dump some value as a JSON string and then load that string interpreted as JSON to a value, it's equal to the value we started with. Does everyone think this property should hold? Show of hands, it should be true. Show of hands, it should be false. You're a suspicious bunch. So the first step, right, we can just try putting none in. And this test passes for none. It turns out if you serialize it to null and then bring that back from JSON, you get none again. So we're all good so far. And then incrementally, we can improve that strategy. We can go, let's look at none or booleans or floats or text. That's Unicode strings. In Python 3, it's just strings. Should this test pass? It should pass. It should not pass. Why doesn't it pass? Floats. There is a special floating point value called not a number, which is unequal to itself. Numbers are equal to themselves, but fortunately this float is not a number. And so again, we can simply add an assumption. So we say for any value which is equal to itself, if we write it to JSON and then read it back to Python values, the new value should be equal to the old value. Should this one pass? Yes? No? This one does pass. But all we're dealing with here is JSON scalars, right? If we have lists or what JSON calls arrays, lists or objects, that is Python dictionaries, we're not generating those and we're not testing them. Fortunately, with hypothesis, we can also generate recursive data. And so this strategy says, starting with null or booleans or floats or text, we can take lists of whatever we have or dictionaries of strings to whatever it is we have. And this recursive definition actually does describe all JSON. And so we feed it into the same thing. Should this test pass? It should pass. It should not pass. I didn't raise my hand. Yeah. This one, it turns out, fails. I didn't know that this test fails until I was writing up a tutorial, and I thought, this will be a good example, right? I'll incrementally write a property-based test, and it will fail, but we'll hit nan, right? And that will show people. It turns out that Python lists, right? Two lists are equal if and only if they're both lists, and then each of their corresponding elements are equal. So a list with nan in it would not be equal to itself, because nan is not equal to itself. But Python has an optimization, where if a list is compared to itself, the comparison happens by identity, because A is A equals returns true. Because not a number breaks Python's object equality model, and so if you run this test, it will duly spit out for you a list with a single floating point, not a number in it. There we are, folks. Sufficiently advanced testing. So, thank you very much.
Brilliant talk. We have about 8 minutes for questions, if there are questions. If you hold up your hand, I can give you the microphone.
Does hypothesis work with type annotations at all? If you know in the code that something is an int, can you automatically generate strategy based on that?
Yes, it can. So if you decorate @given and say value equals infer, and you've type annotated, it will do that. We also have a builds function, which takes some class or function and then strategies corresponding to the arguments for it. If you have type annotated required arguments with no user supplied strategy, we'll recursively infer how to build it.
One here, then one there.
That one was hard to implement across versions.
Thanks for the talk. Can you use async IO and coroutines with hypothesis?
Hypothesis natively only calls sync functions, mostly because it's hard to know what event loop to use. But if you're using something like PyTest async IO or PyTest Trio, they have a plugin which actually supports hypothesis. So they understand how to insert a shim which converts async to sync code for us. So you can write async tests if you use a test runner which supports that.
Sorry, this person was first.
Hi. So it seems like the biggest advantage of this is that you really can go into your testing with very little assumptions as to where the bugs might be found. With the targeted PBT methods, you're then adding some assumptions back in. And so is there any disadvantage to kind of leading your tests down the wrong garden path?
Potentially. So this is one of the reasons I would think of that as a potentially fragile technique, that if it turns out that your thing is particularly vulnerable to very small inputs, but you've targeted very large inputs, it's going to spend most of its time generating things which won't find those small bugs. If it works, right? Yeah. So part of the design would be making sure it balances a little between generating things it's been told to and other less directed exploration.
Follow-up to the annotation question, does it work with protocols such as protobuf or thrift, that like you can infer the underlying interfaces type?
So there is a third-party extension for protobuf. You can hand it a protobuf schema and it will generate messages that are matched by that. In general, we have support for a couple. So type annotations, regular expressions, context-free grammars, a few others. There are more in third-party ones. And of course, if you can do it yourself, you can just write a function which takes some schema of whatever kind and returns a strategy for things that match it. So I don't think there's a thrift one, but nor do I think it would be that hard to write your own.
One there.
Does Hypothesis natively do like operating system testing, or do you have to do something else to get that kind of?
So Hypothesis is really designed for testing Python functions or Python code. You can easily enough write Python tests which then themselves test operating system function. But for compiled code, I'd turn first to something like American Fuzzy Lop, a dedicated machine code fuzzing tool. So Hypothesis does not, by default, test across multiple operating systems. But if you had a function which ran some piece of code on multiple operating systems, you could then use Hypothesis to assert that they all return the same result.
I have two questions. First question is, how do you convince your teammates to use Hypothesis? If you love it and your teammates don't, what do you do?
Install it first. So this one is actually tricky. The most effective way I've found is to migrate just a couple of tests, so spend an afternoon on it. And if you find a bug which your teammates believe is a bug, first get the bug report in. Then tell them you found it with Hypothesis.
And my second question is, I work in a lot of ML, and this is more general testing. How do you go about testing in machine learning stacks and data science stacks in general?
That one is hard, right? This is part of the problem of how do we even know what the correct answer is? Sometimes there are properties you can check. So after each training epoch, for example, you could check that the model weights have changed for every layer. Or you could make assertions about the bounds, that probabilities, regardless of what they end up being, must always be between 0 and 1. Or that adding certain desirable features does not decrease the score when you classify it, things like that. So while you can't test the exact expected output, you can still tell something about, often if you perturb the input, what kind of change do you expect in the output. Especially with machine learning, that won't always indicate you have a bug. It might just be that you've misunderstood your system. It's hard.
We have time for one final question.
Is a question on fuzzing in general. Like sometimes fuzzing can catch a lot of issues, but they're rarely reproducible in production. And it can make the code much more complex and more defensive to basically make testing compliance, but then the value in production is very low. What's your opinion on that?
Sometimes you just don't care about certain bugs. My instinct would always be try to catch that stuff when you're validating your inputs. So whatever the bug is, right, either it is a bug that we care about for whatever reason, in which case it will be good to return an explicit error, or my view is it's not something we should consider a bug at all. Maybe it's behavior that is less than ideal, but my view of a bug really is that it's something we would want to change about our code in order to consider it fixed. So there are some people who dislike hypothesis because it finds all kinds of ways to trigger exceptions that they just don't want to hear about because there are hundreds of them and they already have 1,000 open tickets. I'm sympathetic. I've been there too. Ultimately, no testing, no analysis, no correctness technique is actually useful if you don't want to act on the results. So in much the same way as I would not say that type checking is suitable for every code base, really intensive testing is not always suitable for every code base. But for when it is, I hope you consider some of the tools I've spoken about today. So thanks very much.